Firstly, let's have a quick look at the equipment we need for the test. In this test, we are going to use Tensile UTM, Universal Testing Machine, to break the cylindrical samples. As you can see, this machine is composed of the control units on the right and the testing units on the left. The control units include the manual control console, the automatic control console, which is the computer that with the software to control the testing, record the testing data, and of course, generate the testing report. Also, there is a control panel provides the functions such as starting the hydraulic pump of the machine. The testing units include the hydraulic pump at the bottom. It generates the loads to drive the testing frame upwards or downwards. The unit in the middle is a crosshead driven by an electric motor. We can jog the crosshead up or down to adjust the distance of the fixture for installing the testing sample. Besides the UTM, we also need a tensiometer to measure the strain during the tensile test. Here is a close looking of the 1-inch gauge length tensiometer. It has a rotary knob marked as 0. This is the lock to fix the arm on the top of the tensiometer to the initial position. It means that at the time we grab the tensiometer on the testing sample, the initial measuring length is assured by this lock to be exactly 1 inch. After that, before we start running the test, we need to turn the knob clockwise until the pointer on it upward entirely. Then, the arm connected to the sensor is freed to measure the minor length change of the testing sample when the sample is stretched. Here is the example. The top arm is locked to the initial position now. We also need to check from the side to make sure the tensiometer is installed straightly. Then we will unlock the measuring arm by turning the knob gently to the vertical position. Now it's ready for the testing.
Ladies and gentlemen, as you can see, Mr. Jadong San, the lab manager, is going to start the initial part of the experiment by measuring the area. Now, if we have a rectangular sample, we measure thickness and width. For a cylindrical sample, you measure the diameter, or 2 times the radius. And you take a couple of readings, 3 readings, and you average them. And the number is around about
498.
Yeah, about half an inch. Take or subtract. And then he is going to put 2 markers which will be showing the gauge length, and he is going to record a 2 inches with a 1 inch. Yeah, he's recording, he's marking 1 inch, so that after we break the sample, we want to see how much distance the 2 markers travel. And then we're going to subtract this distance from the original 1 inch and divide it by the original 1 inch. That will give us the percent elongation, which is a measure of ductility. So he measured the diameter. The area will be pi d squared over 4, and then he made a mark of 1 inches along the gauge, or along the length of the sample.
Here is another example of the measurement procedure, measuring at least 3 positions at the middle area of the sample. Record the results, then calculate the average. By the way, don't forget to zero the caliper after you turn it on. Now, we are going to mark the 1-inch gauge length on the sample. Usually, I make 2 more pairs of marks of the center area in case the sample breaks off the center. Here is a sample broke off the center. Now we are going to set up the testing software and install the sample. As you can see on the monitor, we have two windows. The left one is the stress versus strain curve plotting window. The right one is the controlling window, which also has the indicators showing the real-time value of the loading, the testing frame position, and the strain. Then I'm going to install the sample into the fixture. Firstly, I need to adjust the position of the crosshead by pressing the jog down button on the manual control console. You can also do that with the software or the control panel. Here I need to mention that the load applied on the sample does not generate by the crosshead, but by the hydraulic pump. As long as the sample is installed, the crosshead is fixed into the initial position. The pump lifts the testing frame upwards with the top fixture, which generates the stretch load on the testing sample. Now I'm going to install the sample. By the way, before the installation, I actually have reset the load to 0. After the installation, the load shown on the indicator will be the actual load, which cannot be zeroed off. This is very important. The load value is negative right now, but it doesn't matter because we haven't finished the installation, so the load applied on the sample may be compressed load, not tension load. So we will keep tighten the sample gradually onto the fixture. The 85-pound load shown on the indicator is the real load applied on the sample. Well, it's the time to install the extensometer now. Make sure the extensometer is strictly installed on the sample. And also, don't forget to lock the measuring arm before the installation and unlock it after the installation. Then reset the string in the software. We are ready for the testing. After input the average diameter into the software, we can run the testing now. By the way, the sample videotaped in this step is a different sample, so the initial load applied was 186 pounds, but all the testing procedure was the same. Also, the testing frame position didn't start from 0. Don't worry, we mainly care about load and strain, which later are converted to the stress strain curve. Now, all the values on the indicator are keeping increasing. It shows that the testing frame is lifted upwards, so the position value is increasing. Then this movement of the testing frame generates more load, which is stretching the sample. Therefore, the strain is increasing too. On the plotting window, we can see the stress strain curve is generated by the software now. The right line is the calculated modulus, the slope. As you can see now, the curve is the change the direction, and soon it will pass the 0.2% of the string, and then the software will plot another line. So here at the cross, we get the yield stress. To protect the extensometer, when it passes the 1.2% string, the software will alert you to take off the extensometer.
Remove instrument.
So later the necking area will be generated. As we can see here, the necking area should be around here. So there's a very minor curve around the surface, on the surface. Yeah, but later it will be obvious. So on the software, as you can see, because I have already taken off the extensometer, so it cannot measure the strain anymore, but it still keep measuring the stress change. So the stress is keep increasing. Well, here I have increased the speed of the video clip. The actual time spent was about 6 minutes. Okay, so alright, now the sample is broken. So I will jog the first head down, then take off the sample. Later, we will need to measure the final length, input it to the software to get the final results. So as we can see here, we have the cone area and also the cup area. Alright, now we are going back to the table, connect the broken parts together again. You need to try to find the position that to bring him back to the broken point, and then we will need to measure the final length. Okay, the final length is 1.239. Back to the software. Here we will input the final length. Then, as you can see here, we got all the results. So the ultimate stress is 113 KSI. The yield strength is around 90.3 KSI. The modulus is 31,000 KSI. So we have a sorry? Yield is let me see. Yield is 90. Ultimate is 22. Let me see. Not 22. It's 113.5. Yeah. So
And the elongation?
elongation is 23.9%. Yeah. Okay. So then, because the result is, makes sense, so it's a good test. So we just click accept. Then the machine will return to the initial position, and then we can run the other test.